When I wake up in the morning, I brew myself a warm cup of coffee. As I was sipping it like I always do, a thought hit me. Why does this warm coffee taste so good? Hidden in that simple pleasure is a profound law of nature. Everything we see, the invisible microscopic world, and even life and time itself are governed by this law. It's one of the most subtle yet fundamental ideas in physics, entropy. You've probably heard the phrase, entropy always increases. But what does that actually mean? Entropy is often described as a measure of disorder. It quantifies how disordered a system is, and it tends to increase with time. Still sounds a bit abstract, doesn't it? Then try this. Heat flows from hot to cold. Hot coffee cools down, and the ice in iced coffee slowly melts. That seemingly obvious rule is the second law of thermodynamics, the law of entropy. Heat always flows in the direction that increases entropy. Heat is energy. When heat moves, energy moves, and that concentrated energy spreads out. Taken together, growing disorder and the flow of heat all point to one idea. Energy tends to disperse. In the 19th century, Rudolf Clausius formalized the second law of thermodynamics, explaining that energy tends to disperse and become less available for useful work. For example, a car engine burns fuel to run, but most of the input energy is lost as waste heat, hard to recover. Clausius formulated it mathematically. Entropy increases. That is what scientists mean when they say entropy tends to increase. Of course, by the first law of thermodynamics, the law of energy conservation, the total energy in an isolated system stays constant, but the heat an engine dumps doesn't turn back into fuel, just as heat doesn't flow from cold to hot, because that would run against the direction in which entropy increases. So why does everything evolve in the direction of increasing entropy? Austrian physicist Ludwig Boltzmann argued that everything that happens emerges from the random motion of microscopic particles. In other words, entropy is fundamentally a matter of probability. For example, imagine two bars, each made of 8 atoms. Suppose the left bar holds 7 energy packets and the right bar holds 3. The left is hotter. At first glance, you'd expect 2 packets to move from left to right, bringing the bars toward thermal balance. But in Boltzmann's picture, those 10 packets wander randomly among the 16 atoms. That means there will be brief moments when energy flows from the colder bar to the hotter one, purely by chance. In this example, the chance of energy moving from cold to hot is about 10%. Roughly one time in 10, the flow briefly goes the wrong way. So why don't we ever see this happen around us? That's because as the number of atoms increases, the probability of such events drops off sharply. If we increase it to 80 atoms per bar and 100 energy packets in total, the probability of heat flowing from cold to hot drops to about 0.05%. A tiny droplet at the tip of a dropper contains about 1.67 times 10 to the 21st water molecules, just a single drop. At that scale, the probability is essentially 0. Boltzmann defined W as the number of microstates a system can have, and used it to express the entropy S mathematically. The more microstates there are, the more likely the system is to be disordered. Consequently, the system is driven toward greater disorder. Even now, as the universe keeps expanding, the number of ways energy can spread out keeps increasing. In the process, energy becomes more evenly dispersed, and the universe's usable energy becomes less available. One day, stars will cease to shine, and the cosmos will reach a state with no change, where even the flow of time loses its direction. This is the entropic end of the universe, the heat death. In this vast current of entropy, what meaning do we, these small beings, really have? All life seems to push back against the law of entropy. Living things constantly take in usable energy to preserve their structure and order. Of course, in the process, the entropy of the larger system inevitably increases. Yet, even within this sweeping tide of disorder, life keeps generating pockets of order. The key point is, at either extreme, very low or very high entropy, complexity is low. Rich possibilities and diverse phenomena emerge only in the middle, and life is precisely what arises in that complex middle ground, like this warm cup of coffee in my hands. Perhaps it tastes so good because it sits right between order and disorder. So maybe the best we can do is enjoy it before it cools. Delicious.